Have you heard the joke about the broken pencil? If you haven't, don't worry. There's no point to it. I know, that's such a bad one. You should probably erase it from your memory. All right, I'm done. Okay, what's going on, Algebros? In this video, I'm going to show you how to solve a rational equation. Get ready to get funky. First thing we're going to want to do is actually factor this quadratic expression right here. And that will help us identify what to use as the LCM. Talk about why that's important in just a moment. Alright, so we're going to copy some of the other stuff down. 4 over x minus 2 equals negative 3 over x plus 5 plus 7 over, and here's the big reveal, that factors as quantity x plus 5 times quantity x minus 2. Alright, let's go ahead and discuss the LCM. Just got to figure out which pen to use. I think I'll go with the red. Alright, off to the side, let's write LCM, little colon. And in solving a rational equation, I often find it easier to think about what expression is going to cancel out all of the denominators in each of the rational expressions. So let's start with the fraction that's on the left-hand side. If I wanted to cancel out the x minus 2, then, I would need a factor of x minus 2 in front of that. So x minus 2 is going to have to be part of my LCM. Come on now. Okay. All right. So moving on with our middle fraction, so to speak, or the first fraction on the right, we've got negative 3 over x plus 5. If I wanted to cancel out this denominator of x plus 5, then I would need a factor of x plus 5 in front. So x plus 5 is going to have to be part of the LCM as well. Now let's see if that's the minimum amount of factors that we need in our LCM. And to determine that, let's look at our very last fraction, 7 over x plus 5 times x minus 2. If I had this entire LCM expression in front of this fraction, would it cancel out these two factors? And the answer would be a resounding yes. Okay, so now that we have the LCM identified, let's go ahead and put it to work. And by that, I mean we're going to multiply both sides of the equation by the LCM. Realistically, what that means is we're going to put a copy of the LCM in front of all of our fractions to see what cancels out, and then what's left over. Alright, on the left here, let's write x minus 2, x plus 5, right in front of the fraction 4 over x minus 2. Alright, now we're going to put a copy of the LCM. Oops, there we go. A copy of the LCM in front of that second fraction, or the first fraction on the right, negative 3 over x plus 5, plus another copy of the LCM, x minus 2, x plus 5. That's going to go in front of that very last fraction, 7 over x plus 5, x minus 2. Alright, now some fun begins to happen. I know, fun in the math class, right? Who would have thought? But anyway, we're going to see some of these factors from the LCM canceling out with these denominators. So case in point, let's go back to the very left-hand side here. You'll notice that the factor of x minus 2 in the LCM is going to cancel out our denominator of x minus 2. How you would rewrite this is as follows. Let's write 4 in front of the remaining factor, the LCM, x plus 5, equals. Alright, what's going to cancel out in this cluster right here? The x plus 5s. So what's left over is going to be negative 3 times quantity x minus 2. So that's the stuff left over from the LCM. Now here's where the real fun happens. If you look at our last cluster, each factor of the LCM is going to cancel out with everything in the denominator. So not only is the x plus 5 going to cancel the x plus 5 down here, but also the x minus 2 is going to cancel out the x minus 2. And that leaves us left over with 7. And lo and behold, we actually get a linear equation. So if you thought that we went from 0 to 60 in this section of notes, from linear to rational, I definitely feel you on that one. But as you can see right now, there's actually a pretty strong connection between rational expressions and, rational equations and linear equations. Oftentimes, when we're solving a rational equation, it turns into a linear one. All right, so let's go ahead and solve for x. Let's begin by distributing to clear parentheses. So on the left, that's 4x plus 20. And on the right, we got negative 3x plus 6 plus 7. I'll leave the left alone for now, 4x plus 20. But on the right, let's combine 6 and 7 to get 13. Now what I'd like to do is add 3x to both sides. We get 7x plus 20 equals 13. Now subtract 20 from both sides. We get 7x equals negative 7. Last but not least, we'll go ahead and divide both sides by 7 to get x equals negative 1. All right, at long last, the fun and excitement for this example is over with. Of course, if you wanted to see if negative 1 was an actual solution to the equation, you could always go back up to the original equation and plug it back in and see that both sides would equal the same number. By the way, if we somehow got an answer of positive 2 or negative 5, we would actually want to discard that because plugging either of positive 2 or negative 5 into the equation would create division by 0. So if you come across an equation like that, where you get an answer and you plug it back in and you get division by 0, then you're likely going to see in the back of the textbook it simply say that there's no solution. Alright guys, that's it for this video. If you have any questions whatsoever, feel free to let me know. Otherwise, thanks for watching another one of these. Hope you enjoyed the dag joke at the beginning, and you probably just heard my cat Luigi. But anyway, look forward to seeing you all in the next one. Thank you.